it don't matter. Some people, well, welcome to our world. Some people are going to be young. Some people will be here.
So let us start day 5. Yes. That is, we will finish and be halfway through this seminar. And not as far as I had hoped to get, but driving too fast gets reckless and foolish. If there is a mechanism to try and have questions here, I would like to try that, see if I can get some questions, and see if the technology let's try that. So I will talk for a little bit, and then in 10 or 15 minutes, maybe we can try to solicit questions.
The people who is joining in the session can ask you for questions, but we don't have people. So if we have it, they can ask you.
Okay, so we don't have online.
Yeah, no.
Okay, then we don't have questions, at least not without forecasting them. Okay. Basic probability. This is probably the first chapter in whatever statistics book you pick up. Basic probabilities of events, and what I would really hope to get through is some explanation that people can understand of statistical independence and conditional probability, especially conditional probability, because fundamentally that's all that any of the statistical models are doing. It's just conditioning on a probability to tell you a little more of something that you already kind of knew. So, I have some topics. Random variable. And event. Statistical event. And then I hope to do statistically independent or dependent or conditional probability. So I will just say conditional probability is where you help out your information with something else. The probability of being on, I'll do my example. Statistical independence versus conditional dependence, conditional probability, joint. Joint probability distribution is, it's something we need to know, and marginal probability distribution. And I think an event, when statistics things talk about events or outcomes, this is a result of a probability experiment. It's best to avoid that terminology and just go with it. Don't worry about the precise definition of a statistical experiment outcome. But just have in mind that, you know, a single coin flip, you know, that's an outcome of a statistical experiment. There is some result. And with a coin, you can do it again and again and again and get a whole series of heads and tails, or ones and zeros. But I'm not well organized today. Better. An event is the terminology in the very basic structure expressions in probability theory for something that is a unknown random quantity, but takes on a, you know, it is either true or false, and there's, you know, you can talk about probability of that. So I have I'm out of order, but I can certainly talk about the probability. This is the expression in any text. Probability of events is written like probability of event A. And that's just a variable to express this event. You don't have to know what it is. And then probability theory goes, you know, you have basic theorems. Probability of the union of events. There's an event A and an event B. The probability of A union B is, okay, this is where you use Venn diagrams. Sorry. That's like a joke almost, but A, B. Here's the things, the space, the universe that results in A event being true. And this is the universe for event B. And the combination, the union of the two events is that. And if you add this and you add this, you double count, you count this twice. Well, that's all you have to remember, is to think about that intersection when you do. Probability of A and B, A or B, any of this, probability of anything, A or B, probability of A plus probability of B, and then took that, we counted twice, so now we subtract the probability of the intersection. A intersect B. But these are like any axiomatic kind of structure that is, you'd rather not have to deal with all the proofs and things, but it's all just dumb tricks. And if you have real numbers, you probably aren't doing this anyway. Let me just get a nice page somewhere that just lays out those rules so we don't have to, so I don't waste time. Wikipedia.org, page 4 probability. It's got to have the rules here. Just laid out nice, just so I cover them. Okay. No. Okay. Probability A union B equals probability A plus probability B minus probability of the intersection A intersect B. Okay, so the probability of the intersection is the probability of the intersection is this minus this equals that. Let's see, is that right? I just flipped it. We have the probability of the intersection. I'm sorry for this, but if you haven't seen basic probability, it's hard to do the other stuff without giving them this. So the intersection, if we take the union, oh no, that's wrong, and we subtract probability of A, and we subtract the probability of B, we're left with negative that. So I just did negative this, positive that. I did my algebra bad. So the probability of the intersection is the probability here plus the probability of B. So we've got this and this. We've got an overlap on the intersection, and then we subtract what lays on top, and we're left with the intersection. Okay. Oh, yes. Probability of A equals some number. It doesn't matter. And it is convenient to define in the abstract the probability of the complement, the universal complement of A. So the probability of A complement, everything that's not A, is 1 minus the number PA, which is 1 minus probability of A. Okay? The point is not complicated, but important to keep in mind that if you have some set and you have probabilities of events and you cut it in half and you call this A and this A complement, the probability of the whole space is 1, because a probability distribution represents all the outcomes and it adds up to 1. And if you have 40% down here, the complementary space is 1 minus that probability. This, you very often see various quantities in statistics represented as 1 minus beta. And this is we talked about the power. The power is the complement of the complementary probability, where beta is the probability of the type 2 error for a specific alternative hypothesis. But you always see things expressed like this instead of a single variable. So just get used to just that or 1 minus that without needing to think. Yes, mutually exclusive. And mutually exclusive. You have a set of outcomes, like A and B outcomes. They are mutually exclusive if there is nothing that overlaps. these overlap. The convenient mathematical definition is, did I do it with the union? Hold on. Probability of A union B equals probability A plus probability of B minus the probability of A intersect B. This is what we put before. The probability of the union is this plus this minus the double. And you define mutually exclusive if and only if the problem if that's 0. There's 16 equivalent ways of saying mutually exclusive, but there's no intersection. We'll do some examples with dice soon. Oh, did anyone come online? Okay. So I had started today talking by suggesting that we try to do some kind of question-answer stuff with across this live system. Of course, when I said that, no one was yet online. So, but now, I guess we have about 4 people on. I would ask that maybe we could try that in 5 or 10 minutes. That people who are watching can take 10 minutes to hopefully have some question ideas, something to ask a question, and I can see if we can, I want to try to see if this can work to answer questions. So, about at the quarter to, I'll ask again. Okay. Okay. Now, we are now to independent and conditional probability. And so, the probability, is that what I wanted? Okay. Probability of A intersect B is equals probability of A multiplied by the probability of B if, meaning if and only if, by definition, this equals this, if and only if A and B are independent in probability. Which is easier explained by things that are not independent. So how do I do this? I just have to, there's no way to avoid it. Okay. So, now I have to define notation for conditional probability. So, probability of A conditional on B is the notation often used for a conditional probability. And say the probability of A given B is how it is stated. The probability of A given B is the probability of A under the known assumption of B. Oh, you have. And then we get to the intersection. So, this is very easy, and it is very often something that people present with errors. So I am going slowly to try and not do something stupid. The probability of A given B. Probability of the intersection divided by the probability of B. I am right. So, we have a picture here that can show part of this. The probability of the intersection. That's the probability here. A intersect B. And we divide by the probability of B. That's a larger set. But this is not 1. The probability of B in this picture is 0.6. 0.6. 60% for B. A is let's see, 60. 50, 60, 50. 50%. We have 50% here. We have 60% over here. The probability of everything is 1. So we got to have 10% there. I can draw that as draw like this. This is A, that's B, that's both. So we have 50%, 40%, 10%. Now, we consider the probability of A, that's over here, given that B is true. So, we look at the probability of the intersection divided by the probability of B. So, what that does is this is a conditional probability is a restriction on the universe. We started out with a universe that is all of A and B, adding to probability 1. But if we are wanting to condition on B, we are going to restrict our outcomes to things in B space. The probability of A, given that we know B is true. So we're here. This part of the statement says, no, we're not in all of the space. We're in just the space that's associated with event B. And so, this picture thing gives us a probability of the intersection. 10% divided by the probability of B. Right? Don't forget that middle intersection, because the intersection is part of B. 0.6, and therefore the probability of A occurring within the context of B is that divided by that. It's how much of A is in this context. Okay, so there's what? Let's try to do a questions. So, please, I would hope someone can.
We just lost the connection, but it was just like 30 seconds ago.
Okay.
Okay, now you can ask for questions.
Okay. I would like to ask the online folks to please try to ask a question. I don't care what. To see if we can use this through this interface. Live people. There's no way I can wake them up, but. Oh, that's you.
No, you can do it. You can do it.
Oh no, there's another one. I don't know what this one. So, questions or some sort of statement, if someone can try to please use this online interface to I want to try it. They're all just asleep or so is this they would type here and it would show up on the chat?
Yeah, the type, they type. That'll be requested.
Oh, come on, please. Someone give it a try. Asking some question or anything to see if we have a interface that can work. Possibly it doesn't work.
No, it is working.
It is working, okay. Alright, well then everyone's asleep, so that's okay. I got more sleep in college than I ever have. And someone please wake up, Damon. Okay. Okay. Now conditional probability is the start of the horror of discrete combinatorial event statistics. If you wish to get an idea of things that discrete combinatorial probability is the most dangerous thing I know from math to have things that look easy or look like you understand it, that you can do it, and that it is far more complicated than you can recognize. And that is, that is certainly what the probability theory experts would generally say, I think. I mean, people that have been doing it for their life generally think the same thing. A conditional probability of event A given B, probability of this event occurring within the context of this restriction. And we can turn it around and say, this is all you need to know. Everything else derives from, one thing. That's the, A, B, there's a decomposition. Oh, no. I'm confused. Okay. So, we'll do probability of B given A. That's the probability of B within the context of A. So it's this divided by the size of the whole space. intersection, A intersect B, divided by probability of A. So the probability of the intersection in the context of a smaller space. So you get it. It's just the denominator. And then, let's see, how do we mess around with that? So then we would have to go, we flip around to probability of B multiplied by the probability of A given B equals the probability of A intersect B. I just moved that over to get the probability of the intersection in terms of this conditional probability. Now I do it for the other conditional probability. I say the probability of the same intersection, A intersect B, is the probability of A times probability of B given A. So again, I will try and solicit some sort of question to see if we can address anything. And you can, of course, Spanish would be okay, I suppose. Okay. Oh, yeah, so we have those things that are equal. So this is equal to that, and we have, how do we do that to make sense? Probability of that down there, probability of B times probability of A intersect B. Divided by the probability of A and this is the, and we get, oh Christ, what are we doing? B, AB, A, probability of B intersect, probability of B given A is that equals probability of A given B times probability of B over the probability of A. Okay. This is just so you know that there are some formulas and relationships that you hope that you don't need to use in anything that's too complicated. Because axiomatic approaches are confusing. And yes, now, back to the intersection. this is just a little derived thing that is useful when you have the need to flip the conditional probability from B given A and find the probability of A given B. And this is showing that if you know probability of A and probability of B, you can just flip it around with this. Alright. Probability of A intersect B is probability of B times that thing, which I don't want. How do I do that? Times A given B. Probability of A intersect B divided by probability of B. That's not very nice. Okay. Oh well, hell. I don't know. At any rate, events which are statistically independent, which is pretty much the same thing as independent in probability, events are independent when two events. When the probability of A intersect B equals the probability of A multiplied by the probability of B. This case, this equality is the equivalent statement. You have they are independent if and only if that is true. So how do I could do my dice example for that. In this case, our picture, we can put numbers in just to play. Probability of the intersection is 10%. And we are checking, does that equal the probability of A multiplied by the probability of B? Where? Not, obviously. So we have 50% probability of A and 60% for B. 60%, 50%. So we have 30% is not equal to 10%, and A and B, we conclude, are not statistically independent in probability. They're not independent events. We already knew that because there were we were doing the conditional probability and looking at that. So, what did we have for today? Conditional. A probability of A in B space is 1/6, 17%, about. And the probability of B in the context of A space is 1/5, 20%. And let's see. If the probability of A given B, probability of A in the context of B restriction, if this was equal to the probability of A, right? Meaning that the conditional probability did not impact the probability of A. If that was true, then we have independent. Then B does not provide any information in probability information about A. If that was, okay, I got it. So, conditional probability is probably the most fundamental, basic thing that is happening in statistical modeling. I mean, that is the key feature that is underneath many concepts and approaches in statistical modeling, is things that have various approaches to describing something that is a conditional probability, which that conditioning is what is added to provide more information. That's what the statistical models, many, fundamentally are, that's what's happening. Like regression. Any regression, any ANOVA, any t-test stuff, all of that can be considered just ways of expressing a conditional probability that is more informative than without the model. So it's worth thinking about. Okay. Let's just assume, I gotta get rid of that, I think. Let's assume probability of A given B equals the probability of A. And it's a good bet. And so this thing is, we're saying that that's true. Also, it's true that probability of A given B is the probability of A intersect B divided by probability of B. this is always true. This always is equal to that. It's not a if definition. This equals that. It's like that. But it's not always equal to that. If we have this case, this is true when the probability of A is not affected by B. And you're not going to learn anything about A by looking at B. B is a useless thing. It does not help. So, we note that we say, let's assume this is true, and then we look at this, which is always true, and we see, we observe that the probability of the intersection A intersect B equals the probability of A times the probability of B. And this is a very useful thing if it's true. There's a lot of places where you're doing statistics and you are really wishing that you could demonstrate independent events, and therefore you can express the intersection as a product of the two. But you can only do that for when you have statistical independence, where there is no conditional probability for A given B or B given A. Let's see. Let's say this is, again, let's start with this, true, and go to, does this, if this is true, do we know what the probability of B given A is? A doesn't depend on B. Does that mean B doesn't depend on A? That's the rhetorical. So this is probability A intersect B over probability of A. I think we probably go here. Oh no, I don't want any A squareds. This is, I just need to flip it around the right way.